Hello, folks. Happy Wednesday.
Afternoon.
Good afternoon.
Good afternoon. All right, so let's go ahead and jump right in. I know that I've gotten a few emails about assignments and deadlines and things like that. So I think what I'm going to do is I'm definitely reading your emails, so I hear you if you're emailing me. Give me until Sunday to kind of figure out like what's been graded, what hasn't, what's been assigned, what hasn't. And I'll try and be much more clear about what the assignments are and maybe even get ahead a little bit about what to expect. I think what I'd like to do is have the classwork posted on Canvas in advance as far as I can kind of get. That way you'll know going into the lesson, like, okay, these are sort of the important takeaways from the last few days, okay? So that's one of my goals this weekend. So if you have any questions about assignments, please hold off on that. I will get back to you if you have emailed me. And if I don't by Sunday or Monday, then definitely shoot me a second email just to remind me, okay? Other than that, we're going to go ahead and start with section 5.3 today, okay? So very similar format as yesterday. The blank notes are under 5.3 in Canvas, so you can download that to your tablet or print it out or just have it up on a screen to look back at later. And then at the end of class, I'll upload my notes so that you have the blank notes, the complete notes, as well as a link to the video. Now, because the videos tend to be kind of large files, because we're going for such a long period of time, the video won't be immediately available. Give me and YouTube and all the processing stuff about a half an hour to 45 minutes to access that link, okay? So if after like an hour or two you still can't access it, definitely let me know, and I'll go back and just make sure all the links are working properly, okay? All right, so let's get started with 5.3. Okay. All right, so today we're going to be taking a look at 5.3, which is called Logarithmic Functions and Graphs. And it is very much tied into what we did yesterday. You'll find out that these two functions really go hand in hand. The exponential and the logarithmic functions work together pretty frequently. And one of the things that's going to be super important is knowing how to convert between the two forms of the equation, from the exponential to the logarithmic and from the logarithmic to the exponential, okay? So let's get started here with what is a logarithm, okay? So I have a few questions here that I want us to take a look at. This first question is 10 to the x equals 100. And I bet that every single one of you could say, oh yeah, x equals 2 because 10 squared is 100, okay? And maybe I'd ramp it up a little bit and say, well, what's 2 to the x equals 32? What does x equal? And you might have to multiply out 2 a few times, but eventually when you get to 2 to the 5th power, you'll get 32. Okay, so we know that x equals 5. And in this last case, we have 5 to the x equals 125. And in that case, x would equal 3 because 5 to the 3rd power is 125. All right. So I think those are pretty straightforward computational things that as math students, we are pretty good at this point in our academic career. And so what we're going to do is take a look at another way that I could ask you the same question and you would get the same answer, okay? So one thing that you'll notice is that all of these have a base, right? So base 10, base 2, base 5, and they all have a variable in the exponent, x, and x and x. And at the end of the day, I wasn't asking you to do like 2 to the 4th power or 2 to the 2nd power. I was asking you to find the power if I gave you the number. And that, my friends, is exactly what a logarithm is. A logarithm is a fancy mathematical term for the technique to find out the exponent when the exponent is the variable, okay? So another way that I could have asked you the very first question is I could have written this: log with a base 10. So the 10 is a little bit lower than the log of 100 equals x. Okay, so I could have asked you log base 10 of 100 equals x. And if you have your calculator handy, try typing this in, log. And when you type log into your calculator, one of the things it does is it opens up a parentheses for you, okay? If your calculator does that, like mine does, you're gonna type log 100, and then you're gonna close the parentheses. And then you're gonna type divided by log, open up another parentheses, 10, and see what you get, okay? So type in log 100 divided by log 10. And again, most calculators out there open up parentheses automatically. Some of them don't, then you don't need to worry about closing it. But if it opens it for you, make sure to close it, okay? Anybody out there have an answer from their calculator of what log 100 divided by log 10 is?
2.
2. All right. Yep, it is 2. So what this is saying is that 2 is equivalent to x. So x is 2. Okay. Now let's add one more color here. We'll call the number on the other side green. Okay. So when I look at this equation that I typed into the calculator, I have log of the number on one side all by itself divided by log of the base, okay? Now, if we think about what this was from yesterday when we talked about exponential functions, we had a to the x equals y. So when we write a to the x equals y, another way of writing that is log base a of y equals x, okay? If you like the color coding, I find it helpful to think about where the things are and where they went. So this a is the base here, but it is also the base in the log form. And the exponent was here, but it is what the log equals in the log form. And the y value is the thing that is being logged, okay? So let's try thinking about how this applies to the second example. If I asked you 2 to the x equals 35, and you can say that equals 5, another way I could have asked that is log base 2 of 32, and that would equal x, okay? Now, if I want to type this into the calculator, I have log, open parentheses, 32, close it, divided by log, open parentheses, 2, close it. And I'll give you a moment to type those in, but we should be getting 5 as an answer. All right. Anybody able to tell me how I can rewrite the last question? What's another way that I could ask that question?
Would it be log 5, 125?
Yeah, it's gonna be log, and we say base 5, so we know that it's the smaller number, log base 5 of 125, and that should equal x. And if we want to type that in, we'll do log of 125 over log of 5. And we should get 3, okay? I would encourage you to make sure to practice with a scientific calculator, especially for the upcoming exam. You will have access to a scientific calculator, but I want to make sure that you know how to type things in so you're matching the answers that we get here, okay? All right, so the idea of a logarithm, again, to summarize, is that if you have a base that you know and you have an exponent that you don't know, a logarithm helps you get that exponent all by itself. So let's take a look at these 3 questions here, okay? So some important common other numbers that can come up, all right? When we're used to working with whole numbers all the time or positive numbers all the time, sometimes we forget that things could be negative numbers or other kinds of numbers, okay? So this first example has 10 to the x equals 100, 1 over 100, excuse me. And in this case, x equals negative 2, okay? The reason why it equals negative 2 is because if I had 10 to the negative 2, that's the same thing as saying 1 over 10 squared. And 1 over 10 squared will give me the 1 over 100. Okay, so just a reminder of what that negative exponent means. It means you move the term with the negative exponent to the other side of the fraction line. Okay. Now I could write this one using log notation as well. I could write it as log. What's the base in this question? 10. Log base 10, good, of 1 over 100 should equal negative 2, which is our x value, okay? Now we could do the same thing for the second equation. And again, I chose this one because it has the negative answer. It's okay for us to get negative answers. So in this case, I would have log base 2 of 1 over 32 equals negative 5, which is my x value. And then the last one, I included this one because sometimes it's so easy for us that we forget about this one special case, right? So the special case being that 5 to some power equals 1. And if you have a whole number, or it doesn't have to be a whole number, if you have a number here, okay, as long as that number is not 0, and you raise it to the power of 0, you're gonna get 1, okay? And so in this case, I would have log base 5 of 1 equals 0, which is my x value, okay? So all a log is a technique to get rid of the exponent, the unknown variable in the exponent, and turn it into a situation where we can find that exact value, okay? Now, all 6 examples that we've seen so far, they talk about when it's a nice whole number, all right? So 5, 2, 3, -2, -5, 0. But the problems that we're going to take a look at are not going to have nice whole number answers. But I want us to imagine like this is kind of the process that we're doing, okay? All right, so a logarithm helps you find an unknown exponent. And so this idea of the logarithmic form and the exponential form, if it's in an exponential form, you can write it in the log form. And if it's in the log form, you can write it in the exponential form, okay? And so if we color code this to be the same as what we did in the initial one, we have a as our base, okay? And a is our base over here. And then we have our exponent, and that equals the number on the other side. And then we have our answer and the thing that's being logged. Now, one thing I want you to be super careful with is every textbook, a lot of them use a lot of different letters. And so it's really important that you think more about where the variable is rather than what it's called. So you might look this up on a different website or a different YouTube video, and it might have X in a totally different place, but you have to know like what the space is that X is occupying. That's what it relates to, okay? All right, so let's jump right in and start solving some equations. Again, your textbook saves the equation solving until the very last section, but I kind of want to start to build that in so we know why we're doing these things and why they're important, okay? All right, so we're gonna start here with example number 1. And so we've got log base 3 of x plus 4 equals log base 3 of 1 minus x. So what is one thing that you folks notice about this equation?
They have the same base.
They have the same base, yeah. Now this is exactly like the first problem we did yesterday where we were looking at an exponential equation and they had the same base, all right? So this base in both sides is a 3. And so if the bases are the same, what that means is the thing that is being logged, x plus 4, is going to have to equal the other thing that's being logged. So we can actually simplify this equation to say x plus 4 equals 1 minus x. And that's something we can only do when we are looking at situations where the logs have the same base, okay? And so I'm going to go ahead and add x to both sides, and I'm going to subtract 4 from both sides. So I will get 2x equals negative 3, and we're going to get x equals negative 3 halves. Now, just like yesterday, we want to make sure that we take our answers, we plug them back into the very original equation and see if it still works, okay? So this would give me log base 3 of negative 1.5 plus 4 equals log base 3 of 1 minus negative 1.5. And so if we simplify this, it will give us log base 3 of 2.5 equals log base 3 of 2.5, okay? And so you don't even need to put that into a calculator to see that both sides are the same and therefore you have a solution. But if you wanted to type this into a calculator and get a number for it, how would you type that into a calculator?
It would be log 2.5 divided by log 3.
Good, log 2.5 over log 3. Now, if you're writing out your work, you 100% do not need to write parentheses. The only reason I usually include these parentheses is because that calculator does it for us, and I want us to get used to closing the parentheses so we don't end up with the wrong number, okay? And so if we type this into the calculator, we should end up with about 0.834, okay? Now, I would say for thinking about the exam on Monday, 3 decimal places in general is a good place to round to, Okay, 3 decimal places. If you go shorter, you only go to 1 decimal place, sometimes your answer actually becomes pretty different when you plug them back in to check your answer. If you go to 3, that tends not to happen. Okay, so I'm going to encourage us to go to at least 3 decimal places. But on the other hand, you don't have to go crazy. You don't have to write like all 8 decimal places out for me. I don't need to see that either, but let's call 3 a happy medium. Okay.
Can I do 5 out of choice, or would I get points marked out for that?
Sorry, say that again?
Can I do 5 decimal places out of choice just because I prefer it?
Yeah, for sure.
Thank you.
Okay, you're welcome. All right, so any questions on example 1? Okay. Let's move on to example 2, okay? Now, example 2, this is where we see a very classic case log equation, okay? And here's what I mean by classic. I see log with a base of something equals y. So if we think back to that slide earlier, it matches this format exactly. So our goal is to rewrite it in exponential form. That means that it's going to be the base raised to the power of the number on the other side equals our unknown. Okay? That means that our equation can be written as 2 to the 4th power equals x minus 5. All right? That makes sense to everyone because this step is super, super important. Like this is going to be foundational for the rest of this chapter. Okay. So if you were thinking about this in steps, all right, I would go ahead and rewrite it in exponential form. Once you have it in exponential form, right, I'll just rewrite that over here. Now you can solve for x, all right? So 2 to the 4th is 16 equals x minus 5. And all we need to do, plus 5, and we'll get x equals 21 as our answer, okay? So to double check that we did it correctly and that it is indeed a solution, we're gonna plug it back in to our original. And we've got log base 2 of 16 equals 4. And again, if I want to type this side into the calculator, I'm going to type log 16 divided by log 2. And we should get 4. Okay. So this ability to rewrite questions in log form in exponential form is so, so foundational. Okay. So now that we've kind of set the stage for the kind of equations that we're going to be solving, let's go back and talk about graphs and graph transformation. So yesterday we talked about graphs and graph transformations for exponential functions. And we said that for an exponential function, we had a situation where we had a curve that could look like this, right? And then what is one of the important characteristics about an exponential function? Graph.
Growth and decay.
Growth versus decay, good. What are the other features about the graph are there?
The asymptotes and the range, and I'm drawing a blank for the other one. I know what it is. I just x equals y. Oh, y-intercept. Y-intercept.
Yeah, you got it. You got it. All right. So we have the horizontal asymptotes, right? There's one of those. And it has a restricted range because it's only above the x-axis, and there is a y-intercept. Very good. Okay, and we could also draw the decay version of this, but it would be similar except reflected around the x or the y-axis. Okay, so knowing that, let's take a look at some graphs of log functions. What do they look like, and what kind of characteristics they have, and how we can think about what the picture might look like depending on where certain numbers are in the equation. Okay. So we've got our exponential function, okay? So exponential and logarithmic functions are what we call inverse functions, all right? And inverse functions are really functions that undo each other. So for example, if you had addition, how do you undo addition?
Subtraction.
Subtraction, yeah, so addition and subtraction are inverse functions. What about multiplication? How do you undo multiplication?
Division.
Division. So multiplication and division are inverse functions. What if you have a square? How do you get rid of a square?
A square root.
Square root, good. Okay, so square and square root are also inverse functions. Anyone know what the inverse function of sine is?
Cosine.
It's not either of those, though. I understand where that comes from. It's actually the one that looks like this, sine with a little -1. Or you might have seen it written as arc sine. And we just say sine, and then the other one we call inverse sine. Okay, so sine and inverse sine, those undo each other. And that we're going to see again in the next unit. Okay, so there's so many inverse functions out there in math, because if we're going to do something, it's really important that we can also undo that something. Okay, so that's what exponential and log functions do. Exponential and log functions, they undo each other. Okay, and so we have an exponential function here. This one has a horizontal asymptote, okay, and it has that y-intercept right at 1. And then let's take a look at the characteristics of the log function, all right? The log function doesn't have a horizontal asymptote, but it does have a vertical asymptote. And this vertical asymptote has an equation of x equals 0. And this log function also does not have a y-intercept, all right? So this this y-intercept was 0, 1. But the log function, or the inverse function, has an x-intercept of 1, 0. Okay? So one thing about inverse functions is that we take the x and y values and we switch them. That's going to give us a coordinate on our inverse function. Okay? So 0, 1, if I switch those numbers, I get 1, 0. That's a point on the inverse function. Now, we've seen a few cases of exponential functions where we have a base, A or base B, and then a very special case that we talked about at the end of class yesterday where we have a base E. Okay, so remember, E is like pi in the sense that it's a number. And because we have sort of two cases of exponentials, we also have two cases of logs. So a log has a base B, but then this one, okay, y equals ln. So first of all, that first letter is an L, not an I. And I think sometimes folks see it as an I, but it's an L, okay? L for log. But this is really log base E of x. So base E comes up so much that it has its own special notation, which is ln. And you should be able to find a button on your calculator, one for log and a separate one for ln, okay? All right, so we've kind of talked a little bit about the important features of a log graph already. We do have that it has a vertical asymptote, and again, we can sort of color that in right here, or shade that in. And that, again, has an equation of x equals 0. We talked about the x-intercept being at 1, 0. And then this one, the graph only shows up on the right-hand side of the y-axis. So what that means is it doesn't have a restricted range, it has a restricted domain that is only from 0 to infinity. Okay, so there's almost like it's only covering half of the graph. It's the right half, whereas the exponential function covered the top half of the graph. Okay. All right, so this should look pretty familiar because we just talked about yesterday how we have exponential functions and we can move them vertically or we can move them horizontally. And so all of that depended on where the number was in the equation. And so just like yesterday, if we see a number at the end, like a plus d, up and down is exactly what you think. Plus d is going to be moving it up, whereas minus d is going to move it down. Now, because I'm only moving it up and down, it does not change the vertical asymptote, right? Because the vertical asymptote goes this way. So if I go up and down, it's not changing location. But on the flip side, if we have this plus c and it's inside of the parentheses, like it's right next to the x, that's our horizontal shift. And that's going to be the one that is the opposite of what you think, okay? So if I see a plus c on the inside, it is moving to the left. Whereas if I see a negative c on the inside, it is shifting to the right. Now, when I shift things left and right with a vertical asymptote, that vertical asymptote definitely changes. Okay, so this vertical asymptote does change with the horizontal shift. All right. Yesterday, we also talked about reflections and how we could reflect over the x-axis or the y-axis. And so if the minus sign is in the front, it's going to be a reflection over the x-axis, just like yesterday, okay? And if the minus sign is on the inside, that's going to be a reflection over the y-axis, right? So if it's in front of the whole equation, it's a reflection over the x-axis. And if it's right next to the x, it's going to be a reflection over the y-axis, okay? But neither of those are going to change your vertical asymptote. All right, so let's take a look at these two questions, all right? Very, very similar to yesterday again. I'll give you a moment to figure out what transformations are happening. So is it moving up and down, and by how much? Is it moving side to side, and by how much? And this time, I don't want to know about a horizontal asymptote. I want to know about the vertical asymptote. What is the equation of the vertical asymptote, okay? So take about a minute or so to figure out which direction things are moving, and if you can, what that vertical asymptote is going to move to, okay? All right. Who thinks they've got an answer for the first one, for example, number 1 here?
Is it gonna go left 100 and down 200?
Left 100, love it. Down 200. And the vertical asymptote?
100?
If it's moving to the left, we're moving to negative 100.
Negative.
But I also want us to get in the habit of writing x equals or y equals in front of that. So we're going to say x equals negative 100. Okay? So you see a question like this on a test, that's all you need to write. You don't need to draw anything. You just need to tell me how things are moving. But one thing that I am pretty picky on is like this kind of notation. So if all you wrote is 100 or negative 100, I'm not going to give you full credit for that. I need you to know whether it's an x equals or a y equals situation. Okay. All right. So maybe someone else have an answer for number 2.
Is reflected across the x-axis and is moved phi up.
Reflect over x-axis, good, and moves up by, good. And the vertical asymptote?
In this case, 0.
And we want to say x equals 0, okay? All right, good job, folks, on these 2 examples. I know these are the same numbers as yesterday, but that's part of the point, right? It doesn't matter what the function is. The numbers in specific places tell you how those functions are going to move. Doesn't matter if it's exponential or log or quadratic or cubic or linear or sine or cosine. Doesn't matter. Okay, these same locations, numbers in these locations will tell you how a graph moves no matter what function it is. All right, so here's our last example for graph transformation. We've got log of 3 minus x. And yesterday, I made a big deal out of this question for the exponential one. Because I think most of us said, yeah, it's going to have a reflection over the y-axis because of that minus sign, right? But then this is one case where we have to do some extra work to see what kind of transformations are happening. So the first thing we need to do is switch this so we have negative x plus 3, okay? And then who remembers what the next thing is that we need to do here?
Take out the negative.
Yeah, we need to factor out that negative. Excellent. So then we've got x minus 3. Okay. And so from here, we've got our reflect over the y-axis, but we've also got this graph moving in the correct direction, which is to the right 3. Now that's going to be super important because if you want to know the equation for that vertical asymptote, it's going to be x equals 3 because I'm moving to the right 3 units, okay? All right, so that's it in terms of graph transformations, all right? And what we're going to do here is we're going to talk about some general log properties, all right? And when we're looking at these log properties, I really want us to think about where they come from and why they, hopefully, think about like how they make sense to us, okay? All right, so I've got 2 different charts here. But if you see log of 1, all right, doesn't matter what the base is. Anytime you see log of 1, it's going to equal 0, okay? So if you type log 1 into your calculator right now, you should get 0 as an answer. And the reason this is because a to the 0 power or a base to the 0 power equals 1. And that's like one of those questions we talked about at the very beginning where I asked like 5 to what power equals 1? And really I was saying, what's log of 1? And that answer is always going to be 0, okay? A second handy property to know is that if the base matches the number that you are logging, the answer is always going to be 1. And the reason for that is because the question is the same thing as saying a to the first power equals a. Now, sometimes you end up with a same base and the number, but there's a power, okay? So like number 2 didn't have a power, 3 does. Your answer is always going to be that power. And the reason why is because when you rewrite this in exponential form, you'll get a to the x equals a to the x. And so that's like our very first equation that we solved, where the bases were the same on both sides, so we could kind of get rid of that part, okay? And then this last one is really important because it just goes back to that idea that exponentials and logs are inverse functions, which means they undo each other, okay? So if I asked you this, x plus 5 and then minus 5, what would you get?
X.
X, good. And if I said x and then times 5 and divided by 5, you would get
X.
x. So when you combine inverse functions, whatever you put in should be the same thing that you get out. And so that's what this is saying here. You have an exponential and a log. Those are inverses. So your answer is going to be whatever you were logging. Okay? So just some handy numbers to know, handy properties to know, okay? But we're actually going to talk about these again with 2 specific cases, all right? So the first specific case is there's something called a common logarithm. Now, I haven't met you all in person, so I cannot know for sure that this is true, but I think that most of us out there have 10 fingers, and most of us out there have 10 toes. And the reason why I'm bringing that up is because 10 is so common in our counting. And we think about when you learned how to count, you were like, well, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And once you hit 10, you kind of just started that pattern all over again. 11 all the way through 20. And then when you got to 20, you started that pattern all over again, all the way to 30, to 40, to 50, okay? So a common log just means that the base is 10. And it's so common that sometimes we don't even write it. We just write log x. So when you don't see the base and you see the word log, it means that it's a common log and the base is 10, okay? Now, on the flip side, there's something called a natural log, okay? And a natural log is the special case when we have a base of e. And so because it has a base of e, we can abbreviate it with the ln, or log natural, okay? So 2 special cases to know about. If you don't see a base written, it's either the common log if you have log, or it's the natural log if you have ln. But all of these properties here are the same for the common log and the natural log as they were for any base a, right? Log 1 is going to be 0. Natural log 1 is going to be 0. Log 10 is 1 because the base here is 10. And log e is 1 because it's really log base e of e equals 1. Okay? And the same holds true for the other properties. But I just wanted us to see that there's sort of like all these general cases out there, and then there's two that are pretty popular, the common log, which is base 10, and the natural log, which is base e. Okay. All right. So we're going to take a look at some applications of logs. So again, we're sort of diving into those word problems, thinking about how to set them up. And the good news is if you thought yesterday's setup for exponential functions was something that you really understood, that understanding is going to carry through and help you solve these log equations as well. All right. So we're going to take a look at this equation, or this question rather. It says if you put money into a savings account with an interest rate of 4%, okay, and these days that's pretty high. So if you go to a regular savings account right now at a regular bank, I think the interest rates are like 0.1%, maybe 0.2. You can find some online banks, like banks that are only online and you can't go to like an ATM or a branch because they don't have a physical building. Some of those banks have higher interest rates, which is kind of cool because they don't have to pay rent to like rent a space or to have employees at all their different branches. So they actually save money on what we call overhead. So they don't have to pay rent and things like that. And so what they do is they try and attract more customers by giving you a higher interest rate. And I know for some of those banks that are only online right now, the interest rate is about 1%. So 1 is still not a whole lot, but it's a lot better than 0.1, okay? So in this question, we're looking at what happens if we have an interest rate of 4%, which is kind of high, all right, in today's economy. But the question is, how long will it take your money to double, okay? So one thing you'll notice about this question is I intentionally did not put in a number for how much you put into your bank account. To me, everyone's got sort of an amount that like is accessible to them, right? It could be $50, it could be $500, it could be $5,000. You know, maybe you're one of the lucky few who could put $5 million into a savings account. I don't know. But it's intentional that we don't have an amount here because it turns out that no matter how much you put in, if we all put different amounts of money in and we all have an interest rate of 4%, it's going to take us all the same amount of time to double our money. You put 50 bucks in, it'll take you the same amount to get to 100 as somebody puts 5,000 in and wants to get to 10,000. Okay, so let's kind of see why that is. All right, so I see a percent and I know that I have an initial amount, okay? So I have A equals PE to the RT. All right. And again, you could use the BA to the X formula, but that one would only count your interest like every year. Whereas this one will give you a more exact, more accurate to like how banks do it these days. Okay. So let's say that whatever you put in is your principal amount. And I know that E is a constant, so I'm going to put that number there. And then for the R, what am I going to put in there?
4/100.
4/100, good, because we need to make sure we put that as a decimal version of that and not as the percent, okay? And T is what we don't know. That's what we're looking for. How long will it take for our money to double? Now, if I put in a certain amount, okay, let's call this P for principal, how much do I want to end up with?
2T.
Yeah, exactly, 2T, right? I put in $500, I want to see how long it's going to take to get to $1,000. But maybe somebody else wants to figure out, they put in $50, when are they going to get 100? And so from here, one thing I want us to notice is that we are looking for an unknown that is in the exponent. The thing we don't know is in the exponent. That means that even though we're in exponential form, we want to get to log form. We're going to simplify here first. The first thing I want to do is divide both sides by p. On the right-hand side, that will give me e to the 0.04t. All right, and that's because this principal and that principal reduce to 1. What does the left-hand side equal?
2.
2.
No.
Yeah, it goes to 2 because this principal and that principal also reduce to 1. So that's why mathematically it doesn't really matter how much you put in if it's different from your buddy or your parents or your siblings or your friends. It will still take the same amount of time to double. Okay. All right, so it's in exponential form. I want to rewrite this in log form. So I'm going to write log. What's my base here?
E.
E, good. So I'm going to write a little e here. What's the number that is being logged?
2.
2, very good. And that equals 0.04t. Okay. So by rewriting it in log form, look what we did. We got that thing we don't know out of the exponent. Super nice. Now this log base e of 2, I can rewrite as natural log of 2. All right. Now what's the last step I need to do in order to get t all by itself?
5.04.
Perfect. Divide by that 0.04. So I get t equals natural log 2 over 0.04. Now, if you were on an exam, taking an exam and you left your answer like that, that would be fine. You could also turn this into a decimal and round to, let's say, at least 3 places, okay? Could be 5, whatever, could be more, but maybe not less than 3. And so we're gonna type ln, see if you can find the ln button on your calculator. And I think those tend to open up a parentheses too, so we wanna close it. So ln 2 divided by 0.04 gives us 17.329 years. Okay. So at 4% interest, it will take you more than 17 years to have your money double. And that is assuming that you put money into the account and then you totally forgot about it. Okay, it does not count if you continue to put money into it. It's like a one-time deposit and you don't do anything with it. It'll take you 17 years to double your money. Some people like the savings account idea because it's guaranteed money, right? It doesn't matter how bad the stock market is or how bad the economy is. You put that money in there, in 17 years, you're gonna have double. But for folks who maybe wanna invest a little bit more aggressively, that's why some people choose the stock market, because you can get more money if it's going well, but on the flip side, you could lose a whole lot of money if it's not going well, okay? All right, so this is gonna be the last example in this section. After we finish this, we'll take a break. And then we're going to come back, and I'd like to start on the next section as much as we can today, just so that we have enough time tomorrow to make sure that you feel comfortable with the rest of the chapter. Okay, so we'll finish this question, we'll take a break, and then we'll come back and do a little bit, as much as we can do, of 5.4. Great question. Why was the unit measure in years? Because the question was how long it will take for your money to double, and interest rates are usually calculated by the year. Okay, so it's like a 4% annual interest rate. All right, so last question here. This is also a very classic situation where we want to use logs, okay? In fact, it is so classic that it has its own name for this type of problem, which is Newton's law of cooling. Oh. Okay, and there's a formula for that, and we'll write out what that formula is. But let's read through the question first. A cheesecake is taken out of the oven with an internal temperature of 165 degrees and is placed in a 35-degree refrigerator. After 10 minutes, the cheesecake has cooled to 150 degrees. If we must wait until the cheesecake has cooled to 70 degrees before we eat it, how much longer will we have to wait? Okay. So you'll see questions like this where it's like you have something that you took out of the oven and it's really hot and it needs to cool down, and we need to find out how quickly it's cooling down so we can figure out how long we have to wait. Another common twist on this problem is you have your cup of coffee and you want to know how long you have to wait until it's at a drinkable temperature. Or sometimes in more sciencey settings, it might be like you have a piece of metal that was heated up and it's really hot and you want to cool it down, so you put it in some water to cool it down. How long will it take to cool it down? All right, so anytime you kind of hear these kinds of problems, I want you to be thinking Newton's law of cooling, okay? And so here's what the formula is for Newton's law of cooling. T equals T sub 0 minus T sub m e to the minus kt plus T sub m, okay? So lots of different T's here, and it would be important that we know what they stand for. So this T sub 0, here's what this T sub 0 stands for. The T sub 0 stands for the initial temperature of the item, okay? So in this case, what's our T sub 0?
165.
Perfect, 165, okay? T sub m is the temperature of the medium. And the medium here is just talking about whatever you put your object in. So if you have a metal object and it put into some water, then the temperature of the medium is the temperature of the water. If you have a cup of coffee and you leave it in a room, then the temperature of the room is the temperature of the medium. So the temperature of the medium here is going to be 35 because it's going to be the temperature of the refrigerator. T stands for your ending temperature. And so what do we think it's going to be in this case?
70.
70. Okay. Because that's what we have to wait until it achieves that temperature in order to consume this cheesecake. All right. K is our cooling constant. And this number changes depending on the object. So cheesecake has a specific cooling constant. A penny has a specific cooling constant. Our coffee has a specific cooling constant. All of these things have their own specific constant, all right? And it basically tells us how quickly it's going to cool. And then the little t is our time, like how long it's going to take for that thing to cool. All right. So let's take all these numbers that we have, plug them into our equation, kind of see what we have to start with. So I've got 70 equals 165 minus 35 e to the minus kt plus 35. All right. The way the equation is written right now, can we solve it right now?
No, because we don't know what does T stand for. Okay, I start.
We don't know T and we don't know K. So that is the problem right here, is that when we take all the numbers we had and we were able to plug them all in, we still had two things that we didn't know. And this is a very classic scenario with Newton's law of cooling. And so the way we're going to approach this is we're going to split this into two parts. The first thing we're going to do is we're going to find K. And here's how we're going to find K. I know that after 10 minutes, the cheesecake is cooled to 150 degrees. So here's what I'm going to do. Instead of 70, I'm going to put 110. And then I'm going to have 165 minus 35 e to the minus k times 10 plus 35. So what I did is I said, they told me about what happens in 10 minutes. And so I'm going to use that time of 10 minutes to help me find my cooling constant. And then as soon as I know my cooling constant, I can figure out how long it's going to take for that item to cool to the temperature that I want it to cool to. Okay. Are there any questions about where these numbers came from right now?
The 110.
Oh, I'm sorry, that should be 150. Is that your question?
Yeah.
Okay, awesome, thank you. All right, any other questions about where numbers came from? Okay, so let's follow our order of operations and solve for K. So I'm going to subtract the 35 to the other side. So I have 150 minus 35 is going to give me 115 equals 165 minus 35 is 130 e to the minus 10k. And what should I do next to find my k?
Root it by -10.
There's one thing we need to do before we think about getting things out of the exponent.
We do the
Divide by 130.
Yeah, and so here's why. I'm going to leave this screen for just 1 second. Remember how for this question, the first thing we did was divide that p away? So a lot of times that is our first step, okay? So I'm gonna divide both sides by 130. So I have 150 divided by 130 equals e to the negative 10k. Now this is in exponential form. How do I get the k out of the exponent? And our answer should be using logs, okay? So let's, if I rewrite this using logs, I get log base e of 115 over 130 equals the thing in my exponent. Okay, so this ability to write it an exponential form into a log form, that's what gets rid of your exponent, not taking a root. Okay, you take a root when the base is the variable, but when the exponent is the variable, we need to use logs. What's the last step I need to do here in order to get k by itself?
Divide by k?
To get k by itself.
Divided by negative 10.
Yeah, we're gonna get rid of that negative 10. We don't wanna move the k, we wanna move the thing attached to it. So that's gonna give me k equals, instead of writing log base e, I'm gonna write it as natural log 115 over 130 divided by negative 10. Now there's a reason why I haven't turned anything into a decimal yet. The problem with turning things into decimals in exponential and log equations is every time you turn it into a decimal, you round. And then you round again, and then you round again. And what happens is it ends up, all that rounding really changes your answer. So one thing that I really like to do is to leave everything in exact form until I get to the end. So now I'm going to type this into my calculator. All right, so I've got natural log 115 divided by 130, close the parentheses, divided by negative 10. And that gives me a k value of 0.01226, okay? I'm taking more than 3 decimal places here because I know I have to use this number in a second step. So I want to make sure that I'm not rounding too early here, okay? All right, so I found my k value. Now I'm going to continue this problem on the next slide, and I'm going to bring that k value down with us, the 0.01226, okay? So the second step in a Newton's law of cooling situation is now we're going to use k to find t. So that very first equation that we wrote, 70 equals 165 minus 35 e to the minus, we have a k value now, 0.01226 t, and then plus 35. Now the only thing we don't know is t, so now we can solve for it, okay? I'm going to go ahead and subtract this 35 to the other side, and I'm going to turn this into 130. So 75 minus 35 is 35 equals 130 e to the minus 0.01226 t. All right, so we can get our answer in, I think, 2 steps. What's the next step here?
Like
Like
130.
Yeah, divide that 130. So 35 over 130 equals e to the negative 0.01226t. All right, what do we do next?
Rewrite it in solve.
Rewrite it in log form. So I'm going to have log base e of 35 over 130 equals negative 0.01226t. Now, if you want to jump right ahead and write log base e as ln, you are totally welcome to do that, okay? So natural log of 35 over 130 equals negative 0.01226t. And last step here, we're just going to divide by that negative 0.01226 to find out how long we have to wait for that cheesecake. So let's see what we get. I think we get something about 107 minutes. Is that what other folks are getting?
I'm getting 10 point something.
It's 0.01226. Did you type in that? Like there's a 0 here?
Yeah, I got 107.0298, which rounds to that.
Perfect. Okay. So as you guys are practicing, do make sure that you're not like, oh, I'm just going to copy down what she had. Make sure that when you type it into the calculator, you're getting the right thing, because that's going to be part of that whole, like, when you're showing your work on the test. And I want to make sure, like, write out where all your numbers that you typed into the calculator, because what if you type it in wrong? I don't want to take off all the credit. So help me out. Show me what you put into the calculator. And that'll be a really great way to help me make sure I get some extra credit, or not extra credit, but partial credit, okay? So for this one, what are the units for this? 107 what?
Minutes?
Minutes, yeah, because when we were looking at using 10 earlier, we used 10 minutes. And so this time is going to be measured in the same units. So it'll be 107 minutes, or a little bit less than 2 hours before you can eat that cheesecake. Okay? So again, this is a pretty classic problem, and we're definitely going to learn how to solve more complicated equations. But as far as the applications, like the word problems go, these are pretty much how they go. There are situations where they give you all this information, and then the question is like, how long is it going to take? Or find that exponent. Use logs to find that exponent. Okay? So let's go ahead and take a short break. So it is about 1:15 now. Let's maybe be back at 1:20, and then we're gonna stop. I'm gonna stop the video. I'm gonna restart it again, so we'll have a separate video for the next section. Okay? So I'll see you folks back here in about 5 minutes.